In section 3.2, we're going to talk about differentiability. So the ability for a function to have a derivative. How f prime might fail to exist. A function will not have a derivative at a point P, called a f of a, where the slopes of the secant lines, again this is our average rate of change, slope of the secant lines, fail to approach a limit as x approaches a. In other words, when we have a function and we're looking for a derivative at a certain point, the slope of the secant line from one side and the slope of the secant line from the other side needs to approach the same value so that when they are near each other, the slope is the same. That's what differentiability is. So here are 4 different instances where we can have the case where a derivative fails to occur. A function whose graph is otherwise smooth will fail to have a derivative at a point where the graph has one of these 4 things. First, a corner. We talked about absolute value and the fact that at 0 the derivative does not exist. In this case, the left side derivative or limit of the average rate of change is -1, and on the right hand side it's +1. A cusp. This is really just an extreme case of a corner. So instead of 2 lines meeting like this somehow, they are coming down and this side is approaching -infinity for its slope and this side is approaching +infinity. So the slope is very, very steep positive on this side, very steep negative on this side, and therefore we do not have a derivative at that point where x equals 0. A vertical tangent. So again, here on the left side as I come in, my slopes are getting bigger and bigger negatives, and on the right side, bigger and bigger, from the left, bigger and bigger positives until the slope is undefined at x equals 0. And the last case is a discontinuity. So if there's a discontinuity, the slope from one side will not equal the slope from the other side. Well, actually, in this case, the slopes are both 0, but there's a discontinuity, so it cannot exist here. There's a jump. There's a break in the graph itself. So let's take a look at this. We're going to show that a particular function is not differentiable at 0. So this is the function we're going to look at. So the first thing I want to do is find my derivative at x cubed, which is the function when the x values are less than 0. So I want the limit as h approaches 0 of f of x plus h, and I'm going, whoops, excuse me, where was I here? F of x plus h minus f of x. So I'm going to use x's instead of a particular value for right now. Even though we want it at 0, we're going to go ahead and use this. So this is going to be the limit as h approaches 0 of x plus h cubed minus x cubed over h, expanding that polynomial. I'm trying to save myself some room because I've got a picture coming up over here on the right. So the limit of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed, this whole piece is the expansion of that binomial. The x cubes cancel. I can divide every piece by h. So I have the limit as h approaches 0 of 3x squared plus 3xh plus h, and as x approaches 0, that is 3x squared. So the derivative as we are approaching 0 from the left is going to be 0 if I plug in 0 for x. Approaching from the other side, we're going to have the limit as h approaches 0 of f of x plus h minus f of x over h. In this case, I'm using the 4x equation. So the limit as h approaches 0 of 4 times x plus h minus 16 over h. Going to come down to here, the limit as h approaches 0 of 4x plus 4h minus 16 over h. I'm going to, what did I do wrong here? Something. 4x plus 4h. Oh, I'm sorry, f of x, not f of 4. This should have been 4x, that should have been 4x, those cancel, and this is 4 no matter what value I plug in for x. So let's take a look at this graph. So this is the equation of y equals 4x. We know that that slope is a constant, that's what we got. And here, as I approach 0, my slope is 0. So in this case, f prime fails to exist because the left and the right derivatives at 0 do not equal each other. So, a recap. Most of the functions we encounter in calculus are differentiable wherever they are defined, which means they will not have corners, cusps, vertical tangents of points of discontinuity within their domains. That's most. However, their graphs will be unbroken and smooth with a well-defined slope at each point. So what does all this bring us to? Differentiability implies local linearity. A good way to think of differentiable functions is that they are locally linear. That is, a function that is differentiable at a closely resembles its own tangent line if we are very, very close to a. When we talk about a graphing calculator, differentiable curves will straighten out when we zoom in on them at a point of differentiability. This is like the horizon. We all know that the world is a globe, it is a sphere, but when we look at the horizon it appears to be straight. We are looking at such a small portion of that circle that it appears to our eyes to be perfectly straight. The same thing happens with curves. So here is a curve. You don't have to write this picture down. If I zoom in on this section here, trying to get about what the graph looks like, I will get this. If I zoom even closer on this section, I will get this. Now there still is a slight curve here, but it's almost a line, and it is almost the same as its tangent line. So the tangent line at this point becomes very close to the curve. That's local linearity. As I get closer and closer to a point, my curve gets closer and closer to a line. So that's what differentiability is. If a function is differentiable, that implies that there is local linearity at a point on the graph. So on a calculator, the calculator uses very small values for h. We can use the difference quotient, f prime of a, which is, we can use the difference quotient to approximate the derivative. We all know that in order to get the actual derivative, we have to have the limit as h approaches 0. A better way to approximate is symmetric difference quotient. In other words, we're going to again take our point A, but instead of just going a and a plus h, we're also going to go a minus h, and we're going to divide by 2h, so that we are taking the average of these two very small approximations. The calculator uses this second method, so it gets a very accurate derivative for us. We're going to skip that. So, an example of a derivative on the calculator. Get your calculator out. So we want to find the numeric derivative of the function f of x equals x squared plus 3 at the point 2. The calculator will automatically choose a very small h for us. We don't need to worry about that. So go to Math on your calculator, choose number 8, which says n deriv. This is the numerical derivative. You should see something on your screen now that looks like this. The first thing we're going to do is put in our function, x cubed plus 3, then put a comment, and we're going to say we want to evaluate this function for a derivative when our x value is 2. So the derivative of x cubed plus 3 for any x value equal to 2. When we do this and push enter, you should get the value 4. And if we used our derivative formula, you would see that we would get 4. Now the problem with this is because of the method used by the calculator, you will sometimes get a derivative value at a non-differentiable point. You have to be smarter than the calculator. If you use nderiv again, and you plug in the absolute value of x for x equal to 0, it will tell you that the derivative is 0. We know that the derivative is not 0, but the calculator thinks that at 0 there is a horizontal asymptote. There is not. So be careful of using nderiv on your calculator. You need to know your function as well as understanding what a derivative means. So differentiability also implies continuity. This is important. If f has a derivative at x equals a, then f is continuous. We cannot have a derivative, we talked about that before, when something has a jump in it. So one other thing, the converse of this is false. Continuity does not imply differentiability. And we've talked about this as well. Remember, just because a function is continuous, that doesn't mean that it's differentiable. But if it is differentiable, then it is continuous. Okay. One more thing to look at here, the intermediate value theorem. Not every function can be a derivative of another function. Let's not worry about this as much as this. We'll talk about this as we get further into derivatives. If a and b are any 2 points in an interval on which f is differentiable, so I have a differentiable, a nice smooth continuous function, and I have a point A and I have a point B. So at A, I have f prime of A, which is the slope at A, and in this case it looks like a small negative. Let's say, just for the sake that it's negative 1/2. And then I have a slope at B, and let's say that f prime of B is 3. Between A, whoops, I lost my graph. Between A and B, f prime will take on every single value between negative 1/2 and 3. So if this is negative 1/2, it starts to be going down. I get a 0 here, and then I get small positive slopes until I get to a slope of 3. So every value for f prime of x between negative 1/2 and 3 is going to be found between A and B, and that's the intermediate value theorem. So if you know that f prime of A is negative 1/2, and you know that f prime of B is 3, you know that somewhere in between here there is a point that has a derivative of, say, 2, or 0, or negative 1/8, or 1/10. So you can find some values knowing what the derivatives are at certain points on the graph. And again, this is if every point is differentiable, in other words, the function is smooth and continuous. And that will be it for this slide.